Я оборудование. Я вполне оборудован, да, так. Не все про это знают, и не все правильно.
Shall we move it a bit closer, the camera, then it,
think so.
I don't know, but then it will be direct view. Also, this is a bit tricky.
Like this, okay, we can do like this.
Yeah, on the floor. But on the side it's better because then when I'm writing, I'm blocking the view. Yeah, sorry. Yeah, good point. Yeah. 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 Yeah, I think so. Okay, thanks a lot. Yeah, yeah, you can stay there. Okay, so this lecture, yeah, so third lecture, so we will speak about we need to finish something about in the online prediction model in the agnostic setting. So there is an algorithm called weighted majority algorithm, and we will prove a mistake bound on it, and this will show something called bias complexity trade-off, which is very similar to bias variance trade-off in machine learning. Okay, so let us repeat what's the model. So there is a certain let's formulate it as a game, like the seminarist started to do. So there are two players, predictor and challenger, and so they will play a game in rounds. In the first round, challenger will, okay, so the game is defined for a set H of classifiers. So H contains functions that maps some input space X to an output space, and here, so recall that Y is a set of two elements. So we're doing binary prediction now. Okay, and so we are given a set H of classifiers, and the game is defined for this set. And so it proceeds in infinitely many rounds. And first round, challenger will choose an input, and then predictor has to say a label, and then challenger can choose any label he wants. Okay, and then the game is repeated. And we say that there exists a strategy for predictor with at most S mistakes. So there are two parameters. So we say that agnostic mistake bound of H with M mistakes is at most S, if and only if, yeah. So if and only if predictor has a strategy such that he at most S times disagrees. So the predicted label disagrees at most S times with the predicted label. Yeah. So we say that agnostic is at most S if predictor has a strategy where he disagrees at most S times with predictor, provided that H contains some function that disagrees at most M times with the given labels by challenger. So challenger. So if M is equal to 0, then we are in what's called realizable setting. So that means that challenger can give any labels, but he needs to be consistent with at least one function in H. So every round there is an input, and then predictor makes a prediction. Challenger gives some label. He can agree or disagree. But for the sequence of given labels, there must be one function that is in H that is consistent with the labels he gives. That's
okay, so that means like the bound agnostic is 0.
Yeah, if M is 0, then that's the game. He needs to be always active. But if M is non-zero, he might disagree. He might give labels such that all classifiers, for example, are wrong in a given. Well, there are only two labels, so he can just say whatever he wants. But at the end of the game, let us say that if we say that if this is not true, it means predictor loses, then let us say at the s+1 time a mistake is declared, he must show a function that makes at most m mistakes. So we could say that this is a way for challenger to win. And the game of predictor is to win, to stay alive indefinitely, right? So to stay under, to make at most s mistakes forever. So at mistake number s, he basically needs to know the function.
So challenger has m engagement to y and x.
Yeah, exactly. Yeah. But okay, this is how things were started to be explained in the seminar. So, but basically there is no true notion. So labels can be anything. And we are trying to be as good. We want to have s as close to m for all the values as an m. So we want to make strategies like this. Okay, but let's stick with this definition. And then we will prove that there exists a strategy such that this, so we can pick some beta. So for every beta with 0, beta 1, there exists a strategy that achieves the following bound. It has log size of h plus log 1 over beta divided by log 2 divided by 1 plus beta. So we say that this is true if there exists a strategy of predictor that satisfies a certain bound, and we can achieve this bound. Okay, so I will prove this theorem and then give the interpretation. So this is obtained by what's called weighted majority algorithm, and I've written it down there. So in each round, challenger chooses xt, then predictor must make a prediction, and here we will use y equal to -1 and +1. And what is this thing saying? It is the sign of some sum. There will be some classifiers that predict -1 and some predict +1. And we take the sum with some weights. Initially, the weights are equal to 1. So all the weights are equal for all f. So that's an initialization. And then here we have the while loop, because and then we do this loop infinitely often. And then after we get the true, we get the label from predictor, from challenger, we will update the weights. And the weights of classifiers that are right, we keep, and the other ones we decrease multiplicatively. So that's the plan. So note that, so we multiply by beta. And here beta is as written here, some constant between 0 and 1. Okay, if, yes. Okay, yeah, so we use machine learning convention, and the sign of 0 is 1. Okay, so that's the algorithm. And note that if we set beta equal to 0, we have a halving algorithm, because it means that all classifiers that make at some point a mistake, they are removed, and all the other have weight 1. And so then we take a majority vote here if all weights are 1 or 0, just a majority vote in the version space, so we recover. And also in this result, oh sorry, I forgot here the factor m, because it was a bit strange, there was no m here. Okay, so that's the result. And note that weighted halving algorithm is for realizable setting for m is equal to 0. And if we set beta equal to 0 as well, then we get logarithm of 2, and we get precisely logarithm of size of h, the bound we had for halving algorithm. So this is generalization. Okay, so now we will work out the proof, and proof always go in 3 steps. First step, we will we will define. Okay, let me first define WT. Just we will look at the sum of all the weights at a given moment. This equal to sum WFT for F and H. Okay, and so step 1, we will say that W1 is equal to size of H. Okay, that's very easy. It's just by initialization step. All the weights are 1. Then second step, WT plus 1 divided by WT will be bounded by, and here we have 1 plus beta over 2. And this has interesting application. After weighted majority algorithm makes S mistakes, we will have a ratio. We know that, so that T moment weighted majority algorithm makes S mistakes. S mistakes, we have that WT divided by W1 is bounded by 1 plus beta over 2 to the power S. Okay. So after, so each time, well, the second step we will prove, I will do it later in detail. I will say, yeah. So at moment T, so let's consider around capital T, after which weighted majority has made S mistakes. So this is the update of the weight at each mistake. After S mistakes, we get this to the power S. So that's the, sorry, I forgot to say probably, at each mistake. So at around T with a mistake, the sum of the weights drops by this constant strictly smaller than 1. After S mistakes, we will have S such drops. And so the ratio of the weights is like this. And then the third step, so step 2, we still need to explain. Step 3 is that WT, so if in round T, there is one classifier that makes at most M mistakes, then we know that WT is large. We know that it is at least beta to the power M, because sum of weights is at least the weight of best classifier. Okay, and so now we have a lower bound for WT and upper bound for WT. And if we compare these bounds, then we get this formula. So that's just a calculation. Let's do the calculation later. Let's first look at this thing we have to prove. So this one we still have to explain, but maybe you already understand why it happens. I'm checking.
Why the wrong answer is by this?
Yeah.
And the sum of wrong answers is this 1/2. So this 1/2 answers we multiply
by beta. Yeah, right.
So we get one. It was 1/2 plus beta.
Yeah. Oh, okay. Let's just, or it's clear. Should I write? Okay, cool. So then this is done, and so now I have to combine all 3. So we have that WT, so beta to the power S is at least WT is at least n times, and then the sum of this 1 plus beta over 2 to the power S. Sorry, yeah.
No.
Yeah. Okay. And so we work it out. We just take logarithms. Let's take negative logarithms. So we have m, okay, log, I'm using binary logarithms, but it doesn't matter in the formula which logarithm I take, right? M log 1 over b is bigger than log n plus s times log 2, 1 plus beta. Okay. And so now I want the bound for s. Oh, I take negative logarithms. But now we are good. Like we bring this, I think you already see it. So this goes here. And then we divide by log 2 over 1 plus beta. And so the theorem is proven. Okay, if you want me to repeat something, just go ahead. Which step? 1, 2, 3, or combination?
Basically, say that let's say that this algorithm gives us so we assume that exists some s for which in any case we make at most s mistakes. So we consider that this s is here.
So we look that we assume that this algorithm makes s mistakes.
Yes, okay.
Yeah. And we assume that the best classifier makes at most m mistakes. Okay, and then we conclude that this relation must be true. And so theorem is proven because this is what happens. Okay, and so this has a nice interpretation because let us apply it to decision trees. So we've used it already a few times. We will think, so let H, D, K denote decision trees with inputs, or let's fix D, and let H decision trees on with D binary inputs with K leaves. Okay, so H sub K, and we well, we didn't prove it, but it's in the slides and the lecture notes, so check it yourself. There is an easy counting algorithm that says that HK is bounded by 2 plus D to the power K. So then we can apply this bound to decision trees. And just to have an example, let us choose beta equal to 1/2. Then we get some coefficients, but they're kind of like you can simplify a little bit, and so we get that the agnostic sample complexity is bounded by 4 times log of H plus 4 times log plus 4 times M. Okay, and so here now we know a bound for size of H, which is 4K log D plus 2 plus 4M. So here we have that agnostic mystic bound of HK of M is bounded by this value. And so here we have a mistake bound and consists out of two components. So here is a term that grows with the size of our set of decision trees we're fitting. And here is another term that tells you what is the best. So it depends on K. What do we choose for MK? The number of mistakes of the best decision trees. And so this is the upper bound we found. And so let us plot such a typical graph. D is decision trees with D inputs. Yeah, so decision trees, so there are D questions, and then the decision tree says yes or no. Yeah. Yeah. K is number of nodes, including leaves in this formula. To get this formula, so K is defined nodes plus leaves. Well, in theoretical computer science, node also can be leaf. Okay. So what do we get for formula? Let me make some, so we got some graph. Eh? Yeah, that's just some constant to get something clear here. So M, K, M sub. Yeah. M is mistake bound, the same thing here. So we've proven that agnostic. So let's see how it looks like. So let me first plot. So let us plot this as a function of K. So the bigger is K, the bigger are the decision trees we're plotting, right? And so we have the first term, and this will be a straight line. So here we have 4K log D plus 2. And then MK. MK is number of mistakes of the best decision trees with K nodes. And initially, typically, this will be, there will be many mistakes in the beginning, and then this is a decreasing line. And at some point, it must go to 0 because we can fit all decision trees. Well, at least, okay, so it becomes small for a given strategy. And so the mistake bound we get is the sum of these two. I will write it in dotted lines, so it will be something like this. And so what we have is, how should we choose K? So what we see is for small k, there will be the best decision trees will be far off. So there is some bias in this model class. For large K, the best decision trees will be perfect in a given problem. But there is some, the bound is large because of this term. It's kind of overfitting term. And so if you want to deploy H, you need to choose the, so you want to fit sizes of decision trees that are in the sweet spot. So that combine for which the sum is minimal. So here is a value of K for which your algorithm makes a minimal number of mistakes. So this is called the bias complexity trade-off. In machine learning, so they have something similar, bias variance trade-off, but we have no probabilities here. So variance doesn't mean much. Okay, this is kind of partial picture because in neural nets trained with gradient descent, something special is happening. So when you make the net bigger and bigger and bigger, then there is, again, the error goes typically down. And this does not contradict statistical learning theory. They're just kind of different complexity term that kicks in. So that there is a different notion of complexity. So the thing is that neural nets start to become similar to support vector machines with some very special kernel. and there is some margin theory where simplicity is defined in some abstract way, and so there is some theory. I mean, there are a lot very recent theory, but a lot of questions still unanswered. But this second going down for neural nets, so this not for decision trees, but for neural nets, wide neural nets, this is currently investigated, and I will speak about it in the last lecture of the course. And maybe there will be time for optional lecture where I can speak a bit more about it. Okay, so that's all for online mistake model. So now we go to a more general model, which is prediction with expert advice. Okay, but it's very similar as agnostic online mistake model. So what should I can repeat the story I once told. Like I was 18 years and I organized activities for children, like volunteering. And on Wednesday, I have to tell everyone what was activity on Saturday. But at that time, weather forecast sucked. And so I looked to weather websites, and then they say different things. And so then I aggregated somehow and make a prediction whether I will do indoor activity or outdoor activity. And so indoor activity was really bad with these children. They're kind of very energetic people, and there were small rooms. So if I so if it's not raining, I definitely go outside. But if it's raining and I go outside, then they're cold, like they're kind of little, and they they lose their jacket or they jump in the puddles, and always, so very interesting children. Okay, but so I made a mistake, and so I alternate again between making predictions and learning more about the weather websites and the general weather and so on, and so on. And so this is the same thing. And another area of application is when you play on the stock market. So you need to gamble on some stocks, then gain something or lose something. From this you learn, and so on and so on. Okay, so setting is that there are two players. And now I will follow the book from Prediction Learning and Games from 2006. And there the two players are called forecaster and environment. And so again, now environment will just choose a set of any labels corresponding to n experts. Okay, wait. Let me say what are the parameters. So it's more general. So there is again a set Y of labels that we predict, and there is also a set of actions that we can do, and the set of actions is larger than the set of labels. So, and we will make a prediction from the set D. So we have extra powers. We have more powers than Y. And they have to be a subset of real numbers. Okay. And then there are two more parameters. There is N is number of experts. So that's like the number of weather websites I'm looking at. And then there is some parameter T, the number of rounds that we will play. Okay, and the game proceeds as follows. So for T equal to 1 till big T. So we will make predictions, and we will try again to be as good as the best prediction. But now we will have some loss function to measure, to compare our action with the selected label. So environment will choose the true label, and depending on this, we will suffer some. So first we get predictions of the n experts. And then we must say our prediction. And then we get, so what we get is given to us by environment. What we say, we are a forecaster. So then we get a label YT. So they have to be in N. Our prediction has to be in the set D. And then we need to get a label and Y. And then after we get this, we receive some loss. So LT plus 1. So our loss will be denoted by L hat. And it will be LT plus, and we will use some simple loss like this. But also the experts, they receive a loss at T plus, sorry. Okay, and so the goal of the game is to keep the regret below certain bound. And what is regret? So RT is equal to the loss at moment T. Yeah, initially the losses are 0, but that's clear, right? L0 equal to 0 is equal to minimum L IT, I smaller than N. So, all our theorems will be bounds on the regret. Okay, so that's the model. And let us consider something, a very simple example that was already in the seminar. Let us say that we have two experts. Yeah. So all theorem will say that there exists a strategy for predictor to keep regret smaller, and it will be typically square root of the number of rounds. So before we had something linear in the number of rounds, but now we will see that with extra actions, we can push it seriously down. Okay, but let us first look to some obstacles. Let us say there are two experts, and we have Y equal to D equal to -1 and +1. Or let us first say 0 and +1. Okay, then we know we get actually a lower bound on the regret. We can show that environment has a strategy to make regret bigger than T/2. So do you remember how it works? Well, just one expert says always 0, the other says always 1. And so environment will always say 0 and 1, and will always disagree. Okay. So then what is, so our regret will be T, right? Because we will say the opposite label, this will always be 1 because 0 and 1 here. Okay, but what will be the minimal regret of our two experts? The one that always says 0 and the one that always say 1. Yeah. Yeah, at most T/2. So we get T minus T/2 or more, and so regret is at least T/2. Okay, and now just for convenience, let us scale things. So now I've doubled the losses. So I've doubled all these terms because I'm using -1 and T. So that means I need to double the regret. Okay, and so now there is a simple strategy where so let us increase the action space. Let us use Y equal to -1, 1, and let us add 0 to -1, 0, 1. Okay, now there is a strategy for predictor to have regret half, at most half of this, T/2. T/2. And it's quite simple and natural strategy. It's called follow the leader. So let me write it. So we will have y hat t equal to, so there are three cases. We will choose the first experts. So again, there is still n equals 2 experts. And so we will choose, if both experts say the same thing, then we will also say the same thing. And then if they say something different, then we will say 0 in case they have the same the same loss at this point. L1t equals L2t. So if they're both the leader, we will say 0. We will use our extra power. And otherwise, we will follow the leader. That's what the name. Well, actually, it's some specific name for a more complicated algorithm, but it's simplified variant. Follow the leader. And then we will put P G star of T otherwise. And J star is just the best leader. It's argmin of the loss. Okay. And so now, why do we achieve T over 2? So can you already tell? Okay, let us consider the three cases. So in first and last case, the regret never increases. So let's check that we see this. So if both experts are the same and we give the same label, then what can happen to the regret? So if it's wrong, then it will increase, but this will increase by the same amount. If it's right, then nothing changes. So here nothing changes. Also here nothing changes. It's clear why? So the regret of the best leader might change, but then, sorry, if we are wrong, then regret of best leader changes by the same amount. Okay, so then in the remaining case, we go in the middle, and then it increases by at most 1. So why do I obtain T over 2 here?
Because the next term is not equal.
Yeah, exactly. So here in this case, we assume that expert predicts something different. And then in the next round, they must have different regrets. Yeah, so for even T, okay, good point. Yeah. In the notes I wrote for even T, and I forgot to mention, okay.
I think it's not 1, it's plus 1 over half. It's plus 1 half.
Yeah, if it's odd, yeah, even better, yeah. Okay. Yes. So that's simple example. Now there exists an algorithm called randomized weighted majority algorithm. So instead, it's the same algorithm as before, but instead of taking a majority vote by the sign function, we will just answer the weighted value. Okay, so now I will, let us quickly write this algorithm. Or first, let us say what this algorithm achieves. So this algorithm achieves error. Okay, so here is a nice theorem. We will have y equal to 0, 1, and we will have the action space equal to continuous interval delta. And so the claim is that a forecaster has a strategy that achieves regret t smaller than 2 times square root n ln h. Okay. And so we will achieve it through a lemma. Okay, I can just write what's happening here. So we will say, so we will again have weights. Wi1 and time 1 is equal to 1. The proofs will be, and all the proofs in the lecture will be similar. And so we will say here the weighted majority IT times PIT. And so we sum for I equal to 1 till n overall expert. That will be our prediction. Okay. And then we will update the weights. But you already know how the weights are updated, right? The same way. WIT plus 1 is equal to, I will use a constant 1 minus alpha WIT or WIT if PIT is equal to YIT, not equal otherwise. So if they're correct, no change, and so on. Okay. So let us, so I will prove a lemma now. And the lemma says that if alpha is between 0 and 1/2, then we obtain regret. This algorithm obtains regret smaller than 1 over alpha ln size of h plus alpha times Lmin. So Lmin is just short for the minimum of all losses. I will need it many times, so it's easy to remember, right? Okay, so now let us see why the lemma implies the theorem. So it's very easy why we get the theorem. We set alpha equal to ln size of h divided by t. Yeah. Okay.
No, I have a question. What's once again this H capital?
H capital is oh, sorry. Yeah, good point. There is no H capital. Yeah, I mean ln n, the number of experts.
So you have square root of n logarithm.
Yeah. No. Oh my God, I'm messing up. So square root of t, the number of rounds, times ln n. Okay, thank you. Yeah, please be careful. My brain is most unreliable thing in the world. If I start to get crazy, tell me immediately and I have a chance to correct it. But the longer you wait to tell me that stopped working, and, okay, and now it's clear, right? How to get it? Okay, so we get, and then let's write it. RT is smaller than, that should be ln n. Ln n divided by square root ln n over t. Plus L min divided by plus square root ln n over t times L min. Okay, and L min is bounded by t. So in each round we have loss at most 1. And so then we are good, because we get square root t times square root ln, and here we get the same. And that's the factor 2.
But how do you prove
This lemma, yeah, this I still need to,
lemma? Okay,
yeah. Like,
we didn't prove it.
no, we didn't prove it yet. But also we have small trouble here. So do you see there was a case we overlooked?
No.
Yeah, the other side. Yeah, it's about alpha. It might be that this is bigger than 1/2. Yeah, so we might have that that this alpha is bigger than 1/2, or let's say bigger or equal. So what does it mean? So it means that square root ln n is bigger than 2 times square root ln n is bigger than square root t. Okay, so now we still get this answer because of trivial upper bound on regret. So trivial upper bound on RT, we already used it, is at the most t. And because trivial upper bound on L hat is t. Okay, so just multiply this by square root t, and this is true. So by assumption, we have this thing. So this implies 2 square root t ln n bigger than t. And this, so we see, and this is a trivial bound for RT just by any strategy of forecaster. So that's very easy case. Okay, so now only thing I have to do is prove lemma. And again, it goes by 1, 2, 3. So you already know step 1. So 1 W1 is equal to n. 2 WT plus 1 over WT is smaller than something. Okay, we need to work here. Okay, but let me tell you what will be our answer. It will be alpha minus alpha times LT. So the loss at moment t, which will be y minus yt minus y hat t. Okay, and then step 3 will be, what is step 3 again? Oh, yeah, of course, yeah, the biggest weight will be so w at capital T. Oh wait, I'm not finished with step T, because this implies that WT divided by W1 is bounded by exponent minus alpha times L min. No, L hat at T. Okay. Just we multiply this and we get the sum of losses. And then step number 3 is WT is bigger than, so T is 1 round after we made, okay, maybe I should say T plus 1 after the last update. This is at least 1 minus alpha times L min. Okay. Yeah, we start with weight 1, and L min is basically the number of losses. So loss is 0 for expert has 0, 1 loss. Well, so the last round is T, but this algorithm computes extra update, and that's the one we need. No. So we say that the sum of weights is a bit bigger than the best weight, and the best weight starts with 1 and decreases each time it makes a mistake. So the number of increases is L min, because L min is just the number of mistakes of best predictor. Okay. And so now we put 1 to 3 together. And so we conclude that WT plus 1 is bigger than, no. We conclude that N times this thing minus alpha LT hat is bigger than 1 minus alpha L min. Okay. And so now let's take negative logarithm. And so we get minus ln n plus alpha L hat t. Well, yeah, is smaller than ln 1 over 1 minus alpha times L min. Okay. And now we will use formula ln 1 over 1 minus alpha is bounded by alpha plus alpha squared. Like you can check it with Taylor expansion around 0, but it only holds for alpha smaller than 1/2. So I guess alpha equal to 0 is also okay. I don't remember, maybe, okay, doesn't matter anyway, because we choose specific value for alpha. No, it can, yeah, then we get 0 smaller than 0. It doesn't, okay, that doesn't matter. Let's not be distracted. Okay, so this is bounded by L min times alpha plus alpha squared. And now we are done. Because, okay, let me write one more time. What we have is that, so let's divide by alpha. Then we have LT hat is smaller than 1 over alpha ln n plus alpha squared L min. And let us put, sorry, alpha L min, and let us put this one, well, we divide by alpha, let's put, okay, no, let's not do too much, plus L min. And that's what we need, because this we can bring here and we get the regret. So we are finished with the proof. So this is lemma. Okay. And now what we will do is, what is actually one of the main purposes of speaking about prediction with expert advice is to make this algorithm give a stronger version. We will speak about exponentially weighted majority algorithm. And it will, our result will be stronger in two ways. First, we get a better constant here. Okay, I managed to forget this constant at the moment. I think it's 1/2 under the square root. So we get a factor 2 times, okay, we will see it when we do the proof. First, and second, we will have y equal to interval, not just binary prediction. So we will be better in 2 ways. But the proof will follow 1, 2, 3. Except in 2, we will need to use 2 things. We will need to use Jensen inequality and something else, which I forgot at the moment. But let us start with explaining Jensen inequality, and I hope I know what to explain next then. Okay. So, and so but actually I have nice slides, so maybe let's switch to the slides, and then it doesn't matter what I forgot or what not. So But if I switch to the slides, you will not see anything. Okay, I think I will just lose 10 minutes if I switch to slides. So I will just on the board and then we see. Oh, that was stupid. Okay, so there is this thing like, can it happen that a person has average weight and average length and he is way too fat, overweight? Doctors say you need to go and lose weight and do sport and diet and so on. So is this possible for humans? So, well, I look to the curve for humans and it's a lot of big variance. So it doesn't look possible. But there are some nurse sharks. So there are sharks that are extremely well studied because they're not worried when they're prisoned. And for them, it's definitely not possible. So in the lecture notes and in the slides, there are some nice pictures. So, so you can see that this fish grows equally in 3 dimensions. So there is a nice connection between, there is cubic connection between weight and length for these sharks. So it's like, so there is some noise with the big ones. And so if you look to the average weight, it will be quite high because a few fat ones will like dominate the weight. But the average length is somewhere here. And then I made calculations from the graph. I estimated the dots because the raw data I couldn't find. And I saw that a nurse shark with average weight and average length will be 50% overweight. So I don't know whether these animals could survive this if it happens. So average, so shark with average weight dies. And so what does it mean? That is consequence of Jensen inequality. Like if F is convex, then we know that expected value of f of x must be bigger than f of expected value of x. So if x is a random variable, some random point, so random length, then expected value of f of x is bigger than f of expected value of x. It's very common inequality in machine learning and statistical learning theory. So how do you get the proof? Well, this is not so difficult. So f is convex. Use another one. F is convex. So the definition, you remember the definition, right? Of f. F is that if you take 2 points and you connect them, so 2 points on the graph, and you connect them by a line, then the curve is below this line. But this is equivalent by saying that for every x, there exists a c, such that f of x tilde is bigger than c times x tilde minus x, yeah, plus f of x. Okay, and so then if we take expected values here for x, so so we choose x to be expected value of x, right? Then we take expected values, and then this term will disappear. So f of x tilde is bigger than 0 plus f of expected value of x. So we set x, we set x equal to expected. Okay, there is some let us change it to x0 to be more clear. And we choose x0 to be expected value of x. Okay. Then here we have, so when we take expected value over both sides, we will have expected value of x tilde, which is just another name for x, minus x0, which so we get 0. So that's the proof. So to prove Jensen inequality, we just have to prove this little lemma. I mean, it's easy if f is differentiable, but it's solved more generally. But then I don't remember the proof. But okay, it's a technical thing. I will never ask this. It's easy to believe, right? If it's convex, you can always go under the curve with the line. Okay. Yes. So this is Jensen inequality. And in the proof, we will also use, now I remember the other tool, which is Hoeffding lemma. Also extremely important thing. So Hoeffding lemma. Hoeffding lemma is the opposite of Jensen inequality. So here we will look at exponent of lambda x, where x is a random variable. And exponent is a convex function. No, yes, convex function. So expected value of exponent is, we can write a lower bound by exponent lambda of expected value of x. But that's just Jensen inequality. We want the opposite, we want an upper bound for it. How can we get it? Okay. So there is an upper bound, and it is just exponent expected value of x plus lambda squared over 8. But here we assume that x belongs with probability 1 is in a unit interval. So this is kind of like core of everything from it just it is like inside combinatorics, inside almost everything. Whenever you study randomized algorithms in theoretical computer science, you will always use, like, Chernoff bound depends on Hoeffding lemma, the proof. So it just, the lemma is in the proof of enormous amount of things. So here, Hoeffding lemma. Okay. And then, but so this is a tight version, but we will not prove it with this factor 8. We will prove something weaker. So because to prove it is just some calculation, and that doesn't teach us anything. So I will prove it without factor 1/8, and then it's very easy, because we know that exponent of r is smaller than 1 plus r. So this left inequality you have seen, right? And then the right inequality is r plus r squared, but we need to assume that r is smaller than 1. So to prove it, yeah, it's written in the note. It's just some calculation with derivatives. So this is quickly to do. Okay, and now we can sandwich exponent. Then this becomes easy to prove. So we look at, so let us write this. First, let's know that if lambda okay, let us first say that x, we may assume that expected value of x is 0, right? Otherwise, we can shift and it doesn't change the assumption of unit interval. Okay, let's simplify. And here we just have lambda squared that we need to prove. And now we take, so note that if lambda is bigger than 1, it is easy. because x squared, x absolute value of x will be smaller than 1. Okay. Since the expected value is 0, then x cannot become, and x is a unit interval. So if lambda is bigger than 1, then whatever is here must be, right? And so here we multiply lambda with something bounded by 1, and here lambda is multiplied with lambda, which is, okay, so it's clear. So we may assume that x is smaller than 1 and lambda is smaller than 1. But then we can apply this formula here to this thing. So we know that exponent of lambda x is smaller than 1 plus lambda x plus lambda squared. I can drop x squared because we assume this. So this is upper bound. Okay, now let us take expected value on both sides. And we are done. Right, so it is equal to 1 plus lambda squared. And then we apply this other inequality. Also another famous one. So everything we use in this lemma, you will use for all the time in the rest of the course. And if you do research for the rest of your life, at least if you do something with probability. We said here that, okay, I assume that, and then I removed expected value here, just to clean up everything. And then we're just saying that exponent lambda x is close to its second Taylor. And then we go back, and the second Taylor, everything is easy, and we'll see here a second Taylor. Okay. That's it. And now last task is to present algorithm, exponentially weighted prediction algorithm. So, sorry, how it's called again? Exponentially weighted majority algorithm, I think. No, exponentially, okay. Majority algorithm. So, and I think the same will go I at time 1 is equal to 1, and then for t equal to 1 till t, get p1 t p and t. You say the same thing. Y hat t is equal to w I t times p I t. Okay, let me remind you, y is equal to 0, 1 is equal to action space. Okay. And then we get y t. And then we update the weights. And now it's even easier, the weights. Vi t plus 1 is equal to Vi t exponent. Okay, and now I don't remember anymore. Yeah, sorry, I was late in preparing, and the last part of lecture, I couldn't. Yeah, it's exponent. So there is a parameter eta, and for eta, what do we assume? Yeah, it's about all these details. Can be anything, right? Anything at least 0. Exponent, the difference of p I t minus y. Okay. Yeah. And so the theorem is that regret is bounded by 1 square root t over 2 ln n. Okay, remember that we had a 2 in the front, and now we have a 2 in the denominator, but under the square root, so it's much better. Well, it's a constant factor better. And there is matching lower bound. It's in the notes. Also really nice proof, but it's more advanced combinatorics with random walks and stuff. So it's not, you don't need to know it, but I got some students who really find it cool proof and reported my mistakes. Okay, so now let us prove, and the proof is again 1, 2, 3. And I didn't prepare it, so it's a bit difficult to explain. But okay, at least 1 we can say that W1 is equal to N. The 2 we will have some work. That will be WT plus 1 divided by WT will be bounded by, let me check. Exponent. First we need the lemma. Where is the lemma? Okay. We will have RT is equal to L hat E minus L min, and this will be bounded by 1 over eta n plus eta times eta over 8 times t. Okay, and then we get this bound by putting again, so now it's clear. So now there are no assumptions on eta except being non-negative, well, being positive, and now it's clear how to go from here to here, right? Just set eta equal to the square root of the ratio of these two things and then work it out. Okay, so to go here, we set eta equal to square root of ln n divided by t, and I think we need an 8 here, like this. Okay. So then this will be, here we get bounded by square root ln n times t, and we divide by the square root 8, so we have 1/2 and 1/2 here. And the other term should be the same. No, it's obvious. Ln n divided by t under the square root. Then we multiply by t and divide by 8. Yeah, so it's exactly the same. Okay. So in step 2, we will have here exponent eta squared over 8 plus, sorry, t, yeah, x squared over 8 plus, sorry, minus eta. And then we will have the difference y hat t minus yt. And then in step 3, we will say that wt is at